Hey YouTube, so this problem is problem number 37 from chapter 4 from the section on mesh with dependent sources. So let's describe this circuit. We have a 25 volt independent voltage source in series with 10 ohms. We have 20 here, 24 here, and we have a current controlled voltage source. So this voltage source is controlled by this current that goes through this 7 ohm resistor. So that current controls that voltage value. And here we have a 21 volt independent voltage source in series with two 7 ohm resistors. So we're looking for the value, the voltage drop across the 20 ohm resistor. And we're also looking for the power either dissipated or absorbed by this dependent voltage source. Okay, so let's get started. We're going to use mesh to solve this problem. And a mesh is an enclosed circuit elements that don't enclose any other circuit elements in there. So when you look at that, it's very clear that we have one mesh here, and I'm going to call that mesh current IA. Another mesh here, and I'm going to call that IB. And finally, we have this mesh here, which the diagram already gave me a name. We're going to call that I delta. So let's go ahead and get started. We have three, in this case, I see that we have three unknowns and three equations will come out of three meshes. So if I didn't, say for example, if I had three equations and four unknowns, then my fourth equation would come from the constraint equation. In this case, we don't need to write a constraint equation because we actually have three equations and three unknowns. So let's get started. The sign of the first, okay, so mesh at IA, the sign of the voltage is going to be the first, the terminal, the sign of the terminal that you encounter when you're going in the direction that you've defined to be positive. So in this case, I have positive IA entering the negative terminal. So that's going to be negative 25 volts plus. Now recall that the mesh method uses KVL, which says the sum of all the voltage drops in a closed mesh will be 0. So the voltage drop across a resistor is going to be V is equal to IR. So it's going to be resistance times current. So this is going to be 10 IA. And across the 20 plus the voltage drop across the 20, which is going to have a net current of IA minus IB. And all that is going to equal 0. Now, the next equation is mesh at IB is going to be the start at the 20 ohm resistor. So we have 20 ohms of resistance with a net current going through it of IB minus IA plus 24 IB. And the positive current hits the first terminal, which is a positive, so this will be plus 6 I delta. That's going to equal 0. And my last mesh is this mesh here. I've got positive I delta entering the negative terminal of the 21 volt independent voltage source. That's going to be minus 21 plus 7 I delta. Well, actually, the two 7 ohm resistors are in series, so we can just say plus 14 I delta. Notice that this is really one equation and one unknown, and we can easily solve for I delta. But why do that? Let's just build a matrix with everything in it. So we're going to go IA, IB, I delta, and constants. So coefficients for IA from the first mesh equation is going to be 10 and 20, so that's going to be 30. IB, we have a negative 20, and constants, the negative 25 will go to the other side as positive 25. And we have 0 occurrences of I delta there, so we're going to put 0 there. Now, in mesh at IB, we have negative 20 for IA, and then for IB, we've got 20 plus 24 So that's going to be 44. And then for I delta, we have an occurrence of 6. And constants, do we have any constants? We have no constants, so that will be 0 there. And then the final line of our equation, we have no occurrences of IA in the third equation, no occurrences of IB. We have 14 for I delta, and then negative 21 will come to the other side as positive 21. Now let's let our calculator do the work. So we go to our simultaneous equation solver and we say 3 equations and 3 unknowns. We've got 30, negative 20, 0, and 25 in the first line, negative 20, 44, 6, and 0. 0, 0, 14, and 21. And solve. Okay, I'm going to take a moment to make sure my calculator matches what I got the first time around. A, B, and C. Okay, so what I found out, and I'm going to erase this, when I solve that system of equations, we get IA is 1 amp, IB is 0.25 amps, and IC is 1.5 amps. Now that's not the information we're looking for, but we sure need it. So we're looking for the voltage drop across that resistor. Well, voltage is equal to current times resistance, right? So we know resistance is 20. And what is the net current going through that? Well, the net current is going to be IA minus IB. So IA minus IB. Okay. Now how do you know it's not IB minus IA? Because I've defined the direction of positive to be counterclockwise. So that means it's going to go first in this direction of voltage drop. So this one goes through the positive. Since it's a voltage drop, it's going to go through the positive and then the negative. And then IB is going to hit the negative and then go to the positive. And that's how I know IB is going to be the negative in that in this computation. So that's going to be 20 times 1 minus 25.25, 250 milliamps. So 1 minus 0.25 times 20. So the voltage is, V out is 15 volts. And verify that's what I got. Yep. Okay, so the second thing that we're looking for is the power that's either delivered or absorbed by the dependent voltage source. So here's my dependent voltage source. We're looking for power generated or dissipated by the dependent voltage source. So I've got positive IB. That's the only current going through that. Positive IB. Positive current going, and the first terminal that it enters is a positive, so it's going to be positive V of 6I delta. Okay? So the sign from the voltage comes from where positive current enters the terminal. So IB, I just erased it. IB is 0.25, and this voltage takes its value from I delta, right? And then, so it's going to be 6 times, positive 6 times I delta, and I delta we said was 1.5 amps. So we're going to go 0.25 times 6 times 1.5, and it gives me positive 2.25 watts. So that tells me this particular circuit element is receiving a charge from the independent voltage sources, so it's absorbing power. That is it. And since the question, I think this question specifically, it says how much is it delivering? Well, since it's absorbing, it's really in reality absorbing power, you negate it and say, if you were to answer that, how much is it delivering? Well, it's delivering negative 2.25 watts. That's how you would answer that question. But in reality, it's really actually receiving a charge from the closed system. Okay, that is it. Don't forget to like the link on Facebook so that your friends find the channel too. Thanks.